Hello everyone and welcome to today's AGI's GeoWebinar series. My name is Leila Gonzalez and I'll be moderating today's GeoConnection webinar. The title of that is Linking AP Courses and Earth Science Literacy with Departmental Sustainability. Now, just before we get started, I want to walk everyone through a few of our webinar basics. We will be recording the webinar today and we'll be posting this content online for later viewing on our GeoWebinar website. For audio clarity, we will be keeping all of the participants muted for the session. So if you have questions, you can go ahead and type them into the question or chat box on your webinar panel. And during the panel discussion, I will be reading those questions to our three panelists today and let them answer those questions at that point. In today's webinar, we'll be having three speakers discussing the topic of linking AP courses and Earth Science Literacy with departmental sustainability. And just so that you have an idea of the schedule for today, we'll be starting with Jill Karsten from the National Science Foundation, and she will be discussing the development of Earth System Science Literacy initiatives and the way forward. And then we'll hear from Chris Lazaro from the College Board, who will be discussing standards for college success, examining earth science standards for middle and high school students. And then we'll be hearing from Bob Riedke from the U.S. Geological Survey, and he will be talking about two committees in the National Literacy Initiative, a promise of geoscience departmental sustainability. And then we'll close out with a panel discussion between the webinar participants and the speakers. Again, you can ask your questions at any time during the webinar today by typing them into that question box or that chat box. So without further ado, I'm going to go ahead and get started here today. And I'm going to go ahead and introduce Jill Karsten. And Jill, I'm going to go ahead and turn the slides over to you.
Okay, thanks, Leila. I hope everybody can hear me. I'm having a little bit of congestion today, and so hopefully my voice is loud enough and clear enough for you to understand what I would like to say. Mostly what I want to do is provide a little bit of a history and motivation for the development of the various literacy frameworks that have been developed related to the geosciences and earth system science, and talk about some of the opportunities that I see, particularly with the view from DC, going forward, and how those literacy frameworks may be used to support improvement of earth system science education in the country. So the question one might ask is, why have these frameworks been developed? Their origin largely represents the fact that we do not have a very strong geoscience education, particularly within the formal K-12 arena, and that there are a number of barriers to increasing access to earth system science content in the formal education system. I know many of you are aware of many of those barriers. A lot of them relate to standards and assessments and what is or is not included in the curriculum. We also have problems with the fact that there is not an advanced placement earth science course or exam offered. Earth sciences in the high school level is often taught as a remedial science, and there are also issues with regard to higher ed and whether they accept earth system science classes as laboratory credits when during the admissions process. So there are a number of you, and I'm sure most of you have been involved in this in the past, who have participated in efforts to try to change and reform some of those practices in the K-12 environment, but we still have a lot of progress to be made there. The other development that's happened is that formal education has become less of being the only venue in which earth system education is offered. We now see this whole generation of free choice learners who sort of combine the formal and informal environments, and so although standards and assessments can help control what's happening in the formal environment, they have less of a role in driving what gets offered informally. So these literacy frameworks, the intent really was to not so much define standards or benchmarks, but to really define the endpoint of what we would like every citizen to learn about earth system science along the way. Now, it's important to understand what we mean by the word literacy. It's not just a matter of knowing the content. It's also having enough of an understanding to be able to use that in making decisions. And so sort of the common definition in all of these frameworks is that an Earth System Science literate person can understand the essential principles and the fundamental concepts of Earth System Science, sort of the factual basis. They can communicate meaningfully about Earth System Science concepts, so they have enough of an understanding of those facts to apply them in conversation. And then they can make informed and responsible decisions regarding issues related to Earth System Science. And this is important because it suggests that there's enough of a level of understanding that people can take action with that knowledge. And as we all know, these issues are very socially relevant: water resources, alternative energy, climate change, etc. So it's very important that all citizens be literate about these processes. Now, each of the frameworks has had its own history. Some have involved face-to-face workshops, some have been done through online interactions, but they share in common that they have been developed with input both from the scientific community and the science education community. And this has been very important because it's defined not only what we can know and what's current scientifically, but also it's pragmatic in understanding what it's feasible for the general public to understand about these processes. And they've also been developed through a highly iterative process that has led to pretty widespread community consensus, which is very important, and it helps us to speak as a unified community in defining what we think is important for people to know about Earth System Science. Now, I'm not going to go through the next several slides in great detail, but I thought it would be helpful to have for you in one place the list of the big ideas related to the four main literacy frameworks: ocean, atmospheric science, climate, and earth science. And as you can see from the example here with the ocean literacy, there are, in most of these frameworks, 7 or 8 big ideas, very fundamental things that capture the main content that we feel everyone should understand. Within the frameworks themselves, each of these big ideas has several supporting fundamental concepts that one needs to know in order to get the big idea. And I'm not going to get into that level of detail, but I have given you on the bottom of the slide here the link to where you can find this framework if you are not familiar with it. Also, as I mentioned, these have been developed through a consensus process. For each of these, at the bottom, I've indicated the main supporting partners who were involved in the development. So for ocean literacy, you see National Geographic, NOAA, the Centers for Ocean Science Education Excellence, National Marine Sanctuaries Foundation, National Marine Educators Association, and the College of Exploration were all involved in the process that led to the adoption of this particular framework. Now, the ocean literacy framework was developed in part because the community felt that there was not enough content related to the ocean in the National Science Education Standards, and so they were one of the original frameworks to be developed. And they have subsequently gone on to develop the scope and sequence and have many more resources that are targeted to this particular framework. So I encourage you to go to that website to see what else has been developed by that community. Atmospheric science literacy, this has been developed through the UCAR, the National Earth Science Teachers Association, NCAR, NOAA, Cooperative Institute for Research in Environmental Science, American Meteorological Society, American Geophysical Union, and NSF and the National Association for Geoscience Teachers. Again, a very broad spectrum of scientific and education communities. Again, I've identified the links at the bottom for where you can get more information on how this literacy framework was developed. Now, excuse me, the atmospheric science literacy framework was developed to complement the climate literacy framework and really address those components of atmospheric processes that were not specifically addressed in the next framework, which is the climate literacy framework. And this has been developed through, largely led by NOAA in its development, but through the course of the process, it ended up being endorsed by the 13 agencies of the federal government that are participating in the U.S. Global Change Research Program. And there are another 20 other organizations that have signed on as endorsers of this framework. and again, a link at the bottom. The fourth of these is the Earth Science Literacy. It came out in 2009. Again, 9 different, I think it's 9? Yes, 9 different big ideas, multiple supporting partners, a website, frame of reference. And what we have now with these 4 frameworks is the core of what could be integrated into an Earth System Science Literacy framework. Each of these groups was developing a framework that would serve a subdiscipline community of the geosciences. They had to obviously run into some boundaries about the content. So, you know, when you start talking about ocean literacy, it's very hard to get at, you know, the rest of the hydrological cycle. Similarly, with the Earth Science framework, they were talking about mostly land and freshwater hydrology, but that obviously is hard to talk about too deeply without thinking about what happens with the connections to the oceans. So ultimately, we want to weave these together into a single unified Earth System Science Literacy framework. And it shouldn't be too hard because you will find in each of these some really common themes that are found in each of the big ideas that are articulated in those frameworks. Those include the fact that there's the process of science, that we understand the Earth through observation, theory, and modeling. There is this idea that Earth's behavior is controlled by the interaction amongst its systems and the transfer of matter and energy between those systems. And this leads to the fact that Earth is dynamic. Its processes vary over time and space. Very important in all of the frameworks is the relationship of living things to physical Earth systems. The fact that life on Earth depends on the processes that happen within the physical Earth, and that humans in particular are you know, users of Earth processes. They're affected positively in terms of resources and negatively in terms of hazards by the processes that shape the Earth. And then finally, that living things, and in particular humans, are capable of changing the Earth system. So these are, you know, the sort of overarching big messages of those frameworks. Now, how are they being used? They are being used in a number of different ways, but I think the essence of it is that they form sort of the main core messages of what people need to know. And they, as I said, they can be used in formal and informal learning environments. They provide a building block for what we hope will be ultimately an integrated Earth System Science Literacy framework. So there would be just one Uber framework. They are endorsed in strategic plans for example, NSF's Geosciences Directorate education programs, this GeoVision report that's referred to on the right. They have been used in guiding the development of educational resources, textbooks, curricular materials, as the core messages that those resources are intended to convey. And now, increasingly, they are being cited within NSF, NOAA, and NASA solicitations related to geoscience education as sort of a required frame of reference, so that resources that may be developed through awards made by those programs are helping to reinforce the messages that are in these frameworks. Now, we have some opportunities, and you're going to be hearing more about these in the next couple of talks that relate to how to use these. We have an administration that is very strong about science and technology, and a lot of that interest is focused on issues that are highly relevant to geosciences: climate change, clean energy, green jobs, etc. The administration is also very interested in advancing STEM education reform, and is actually putting money into offering incentives through programs like the Race to the Top Fund and Educate to Innovate that may help to encourage some fundamental change in practice, particularly in the formal education environments. One of the really important drivers and opportunities that we have is the focus on climate change. I think we're beginning to see that manifested through direct funding lines for climate change education to NSF, NASA, and NOAA. NSF in last year and this year is receiving $10 million for that program each year. and it's about that level for NASA and NOAA as well. So this is a significant investment, recognizing the importance of this issue. And as you know, climate change is really sort of the archetypal Earth system science subject matter, because you can't really talk about climate without bringing in the land, ocean, and atmosphere processes and the relationship between them. And so many of the things that are being supported with regard to climate change education are focused on climate change, but they really cannot be, you can't really educate people about them without addressing some of the broader Earth system science phenomena. Now, in 2009, NSF issued a Dear Colleague letter to establish a strategic climate change education portfolio. And within that, it specifically identified addressing some of the local and national STEM education policies for teaching about climate change as one of its priorities. And I think you recognize that this opens the door to further change at the local levels with regard to Earth system science education. We also were required with the 2009 money to consult with the national academies, and one of the awards made was for establishing a roundtable at the National Research Council on climate change education, intended to basically help provide some guidance to the federal agencies about where the needs are and where the priorities should lie, excuse me, with regard to investing this CCE money. Again, there's specific language in this award related to the STEM education reforms. And so I think these are some wonderful opportunities for us to carry these messages that have been developed in the literacy frameworks and piggyback on some of these STEM education reform efforts to get those messages into the hands of the people who really need them. You may be hearing about this new Common Science Education Standards Initiative. Again, this is an opportunity for Earth Systems community to be at the table in talking about what changes need to be made with regard to what content is being offered in the K-12 curriculum. The goal of this effort is to develop a conceptual framework of disciplinary and cross-disciplinary core ideas for K-12 science standards. The first meeting of that is happening later this week. There will be other opportunities for participation, and I've included the webpage at the bottom there for you if you're not familiar with this opportunity. It is really important that earth sciences be part of this conversation. We'll be hearing just a moment from Chris about the College Board science standards, so I'm not going to dwell on this in particular right here. So what are my final slide here, what are the next steps? As I said, I think it's really important that we keep Earth system science in the conversation. There is an increasing emphasis in the discussions that I've heard both at the K-12 and the undergraduate level that the science that students need to be exposed to is increasingly interdisciplinary. It seems like a wonderful opportunity for us, but most of the people having that conversation are disciplinary scientists, biologists, chemists, physicists, mathematicians, computer scientists, engineers. We need to remind them that Earth system science is a wonderful opportunity to imbue the curriculum with that cross-disciplinary frame of reference. We need to continue to use the frameworks, the Earth system science frameworks, literacy frameworks, to provide those core consistent messages so that our efforts are synergistic and magnified rather than diffused, I guess. I hope that those who are listening will help, become engaged in efforts to translate some of these national policies that are coming down the road to the local practice, because as we all know, that's where the education decisions get made. As part of that, there's a need to help prepare our educators to use these new interdisciplinary curricula, use the frameworks, help get them to a level of comfort that they can understand and implement those literacy framework ideas in their own classes. Similarly, there's a need to get these big ideas from the frameworks into the assessments that tend to drive many of the practice at the local level. So I'm going to end there, and I look forward to our later discussion. Thank you very much.
Thank you very much, Jill. And we're going to go ahead and hand the slides over to Chris Lazaro from the College Board, and he will be speaking about Earth Science Standards for middle and high school students. So Chris, when you're ready, go ahead and take it away.
Okay, so my slide should be up there. Okay, here we go. So I'm going to start today just by giving a general overview of the newly released Science College Board Standards for College Success that were published in September 2009. And then I'll spend a bit more time going a little more deeply into the earth science portion of the document. So just to start, the College Board Standards for College Success. The College Board has created standards in English language arts, mathematics, and science now, with the goal of increasing the number and diversity of students who are prepared to succeed in college. So most people, when they think of the College Board, they think, excuse me, of the SATs or the APs. But specifically, this project was really trying to define college readiness in science. And what we mean by college readiness in science is really David Conley's definition of college readiness, that a student should be able to enter into a college-level science class and not need any remediation. We also set out to provide teachers, school districts, states with a model set of standards. These standards take into account the most recent research in science education and cognitive development. Research such as the NRC's report on taking science to school, as well as AAAS's benchmarks for scientific literacy. They also articulate a way of knowing or understanding. And what I mean by this is that we really set out to outline a clear and well-developed science practices that are integrated into the content of each discipline. And I'll talk more about the science practices in just a minute. So what we really focused on when we were developing the document were the knowledge and skills, again, that model set of standards, increasing the rigor. Now, this is kind of a controversial one because everybody has their own definition of what we mean by rigor. But in defining rigor, the Science Standards Advisory Committee, the group that was working on us with this, really sought to shift the meaning from a focus on learning all of the facts and specific examples about a concept to an understanding and really the application of core principles of the discipline. That it's that idea of practicing science like a scientist. And the next one there, assisting teachers. So, sorry, I just have to move this box. Offering valuable insights and guidance to teachers by describing how students are expected to use and build their knowledge, while at the same time allowing for curriculum to be tailored to the specific needs of students at the local or district level. You'll see that if you look through our document, there's a level of specificity there. I mean, it's a dense document, and really what we're trying to do with that specificity is provide guidance for the teachers while still allowing them kind of the bottom-up curriculum development. We didn't want to kind of cut off that bottom-up curriculum development, so that was very important. So we also had several leading frameworks that helped inform our work on the standards. And the first one there, the College Board AP Science Redesign and Course Frameworks, that was really the biggest influence on our science standards. So what we were trying to do was back map the newly redesigned courses for each of the AP and say what would a student really need in order to meet this goal at the high school level and then again at the middle school level. And again, we also looked at AAAS's benchmarks for scientific literacy, some of the PISA frameworks, as well as the TIMSS frameworks also. So there was some international benchmarking that went on. Development of the committee and the diversity of the standards committee and our reviewers. So we had 5 different committees working on this standards project. We had learning specialists, chemistry, physics, earth science, and biology people. And each committee was composed of middle school teachers, high school teachers, scientists, professors of science education, as well as national professional organizations. Throughout the 3-year process, we also went through several external reviews, and that's Those are the groups here so that you can see this was very well vetted, this document. So here's how this is how the College Board standards really differ from other frameworks. The Science College Board standards really target college readiness as an end goal as opposed to the more general scientific literacy. And what we were really thinking when we were building this is that scientific literacy seems to be a very broad goal. It's difficult to really define a student as either being scientifically literate or scientifically illiterate. And so what we decided to do was think of scientific literacy as kind of the universe of all scientific knowledge, and college readiness is a bar within that knowledge. And that's what we were trying to set. The other thing that really sets us apart is the outlining of the clear and interdisciplinary scientific practices. And I'll show you a couple of examples of this in just a minute, but this is how students should engage or approach science as a scientist. And you'll see an example of that again in just a minute. This is the organizing structure of our standards. So what we set out to do, we couldn't define, these are not courses, because we couldn't say that in 6th grade you're going to have these 3 courses, or in grades 9 through 12 you're going to have these 4 courses. But it's the knowledge and the skill that is kind of embedded in each one of these that we've outlined. So at the 6-8 grade band level, we have earth science, life science, and physical science. And then at the 9-12 grade band level, we have earth science, life science, chemistry, and physics. And then together, all of that knowledge aligns to the AP or college level works. So we have AP Environmental Science, AP Biology, AP Chemistry, or AP Physics. It's important to note here that it's not a linear progression. So you can't just take a life science class at the 6-8 grade band, another one at the 9-12 grade band, and then be expected to jump into AP Biology. You really need to go through all of the content and skill that's outlined in the 6-8 grade band, the 9-12 grade band, to be prepared for any one of those AP or college level courses. I don't want to spend too much time on this, but again, just some of the organizing structure and that level of specificity that I was talking about before. We have 3 grain sizes within the standard. So we have the standard itself, which is the largest grain size, which represents the core knowledge or the overarching ideas of each discipline. The next level down would be the objective, which is really targeting the understanding for the student. And below that, the smallest grain sizes are performance expectations and our essential knowledge statements. The performance expectations are really specify what the student should know or understand, and it provides the teacher with the observable evidence that they would need to see from a student in order to prove that they understand the objective level. And again, I'll show you an example of this in just a second. And the essential knowledge statements really just describe the conceptual targets. They're much more content-based, and they don't integrate the science practices with the content. They're just simply the content themselves. This is the earth science outline of the standards. This is not the standards document, but this is just simply an outline showing the 5 standards as well as the objectives that fall underneath each one of those standards. So for example, you'll see standard 2, Earth is composed of interdependent and interacting systems, and then you have 5 different objectives: atmosphere as a system, oceans as a system, lithosphere as a system, climate, and planetary evolution. So these are the 5 standards that we have. A couple of things to note. The first is standard 5, humans and the environment impact each other. This is something that Jill talked on in her discussion. And I think it's really important to point out here that we were concerned about, as human populations and per capita consumption of natural resources increase, so do humans' impact on Earth systems. And we really wanted to get this across to students because many of these human impacts on Earth systems are not reversible over human lifetimes. And that's something that I think most students don't think about. And we really wanted to have an entire standard really devoted to that. Also, you'll notice that we don't really outline any astronomy topics. This was maybe a bit of a controversial decision, and certainly something we didn't take lightly. But the original charge of our committee was to increase the depth and decrease the breadth. So certain concepts had to be left out. And we felt that the astronomy concepts that we would have put in here did not necessarily align to any of the AP courses that we have, so it was one of the things that did get dropped. So here's an example objective. This is objective 2.2. I'm going to just jump back to the other slide for just a second. This is oceans as a system. And you'll notice here that standard 2, here's standard 2, and oceans as a system falls under standard 2. It's one of the objectives. So going back, students understand that Earth's oceans act as a system that absorbs and distributes matter and energy. And one of the performance expectations that you would find under this objective is describe the chemical processes of limestone formation in seafloor sediments. And then there's also 2 sub-bullets to this performance expectation. Identify the variables such as water temperature, CO2 content, and salinity that control the rate of sediment deposition, and then this predict below it. And here's where you can actually see what we're talking about when we're saying that we're integrating the content and the skills. So you'll see that we have describe and identify and predict. This is really how we want students to be engaging within the content of this particular objective. And if a student can do this, if they can describe the chemical processes or identify the variables or predict how seafloor sediment deposition, then it's kind of providing the evidence to the teacher that the student understands this objective. I'm not going to spend very much time here at all, but the standards and curriculum alignment work is something that we're hoping to do with this document, and we're preparing to do that. So we'll be using this document to align to other state standards and other frameworks, as well as establishing a presence at key conferences. And that very last thing there, Jill had mentioned, which is the National Science Framework, or the Common Science Standards. And this document is helping to inform some of the early dialogue on national standards that's being convened by the National Research Council. And with that, I think I will pass it over to my colleague, Bob Ridke.
We're going to go ahead and pass things over to Bob Ridke next. And just one moment here. Bob, when you're ready, go ahead.
I'm ready. And
there you go.
Well, thanks for the opportunity to bring a few things forward here. And one of the things, working with my colleagues Chris and Jill on a number of these elements, what I'd like to bring forward is my particular thrust on this, and that is what it means to geoscience departments and their health and well-being. I have a vested interest in this, obviously, whether or not one is a scientist in a federal agency or whether one is an academic, or whether or not you're in an organization, a geoscience organization. There are certain common threads and needs and health and vigor that needs to go forward. So I'd like to talk about some of that and the basis. My colleagues talked about some of the literacy initiatives and, of course, the science standards for college success report. These are very lengthy and they're in-depth. And one of the things I'd like to do is to bring forth some of the principles. What drove this forward? And one has to really look at a very important report that came out some years ago, 2002, by the National Research Council, Learning and Understanding. And in that report, that was really a diagnostic, clinical, evaluative kind of report on the international baccalaureate programs and the AP courses, a couple of themes came hammering through here, and that is that students in many of these courses were covering a lot of topics, inch deep and a mile wide. And they were hit heavily on that because advanced placement, by its very name, implies that there should be some depth. There should be mining down. And so you found in this report, curricula for advanced studies should emphasize depth of understanding, not just a lot of factoids to get ready for a test. And this was also language brought forth what we knew 30 years ago during the golden era of science education reform and science in general in the States. These operative terms of engaging and inquiring, experiment, analyze, making conjectures, solving problems, these are all the habits of mind that the review committee that looked at these programs felt was dramatically underrepresented and sadly missing. So these are important things to keep in mind, and this was such a shot across the bow that the National Science Foundation put money into these reform initiatives for many of these courses, and there were 4 science courses: biology, chemistry, environmental science, and AP Physics. AP Physics B. Physics now has a couple of other components to other letters that only physics knows how to do, but we were particularly interested in the environmental science, and there was some sense right up front that maybe bring forth earth and environmental science, because these were the 4 courses. We didn't have earth science. We don't have an earth science AP course. And on that review commission, there were 7 environmental scientists who were familiar with the environmental AP program, and 5 geoscientists, I was one of them, that were brought into this, this AP redesign. What's really interesting about this in our deliberations and our discussions is that the AP environmental science revision, it's not out in press. There's drafts of this, so these are things that you can actually pull up at the moment. But it's a long document, the Earth Science Environmental, or the Environmental Science Program. It's a 115-page document. And it kind of followed what many of these standards reform initiatives, the procedures and overall directions that others have followed, the unifying concepts, sometimes called, you know, the thematic threads and of these models and systems, continuity and change. We wanted some common themes that work through the entire program. And concurrent with that, actually, are some of these big ideas. What are the big ideas that that you're trying to accomplish, that you're trying to instill understandings of? And underneath that, of course, are essential knowledge statements, the fundamental understandings, and they're very elaborate. They're very detailed. Through it all, it's the habits of mind, what was mentioned earlier, how we approach, having the bull detectors out, questioning of all things, validating, getting the reproducibility of your science, but mostly that engagement, trying to move from informing, which we do so much of, and probably will, sadly, to involvement, involving kids in the scientific process. And that goes under all kinds of terms on discovery, learning, hands-on, all those terms, that active engagement and so forth, to get back to that model that has been lost. Now, what we found in working together, the geoscientists and the environmental scientists, is that's really 2 different communities. And you get maybe a little feel for that a little bit under human actions, human beings dependent on ecosystems. This is all terrific stuff, but from the standpoint of the environmental side, it was pretty much a social science bent to it, policies and so forth, where these processes were mentioned, but not to the depth that the geoscientists felt particularly comfortable with. But it all worked. Everything was copacetic during our time in developing this, but it also became very, very evident that there is a very distinct difference. We want to understand in greater depth what those processes are. What makes carbon dioxide a greenhouse gas, or methane? Not just it is a greenhouse gas. We want to know more about some of these tectonic processes, not just the results and so forth. So this was a very interesting understanding, I guess, and awareness of that. Now, as we, here's my iconic professorial individual here. What does this have to do? Why should the faculties of departments or people at our federal agency, scientists and so forth, why should we care about all this? And this kind of cuts to the heart. One is that it is indeed a critical national need, and Jill alluded to some of that in her talk. It's also, and I'm going to try and show this a little bit more here shortly, it's a very critical discipline need. It's absolutely critical for the geosciences. It also gives what many have called, Carnegie Commission has called for this for many, many years, the needed expanded view of the professoriate. What is your role as a professor? And of course, this inherent importance of the integration of education and research. I'm going to focus on that last bullet a little bit more here. And this is, in many ways, my central premise, that education and research are always in the social service. Both are inextricably bound, inherently linked at all levels. We lose that understanding. We certainly had it throughout most of the known ages when science was productive. It has to have benefits. People have got to understand it. There's an educational component if your science is going to do well. If your education component isn't doing well, your research is going to take a wallop. So this is really what we're all about, and why some of the constraints that we're facing in dealing with this linkage, we have to consider the student pool from which we draw upon and which we are ultimately dependent. This is the farm teams, and every single endeavor. You know, it's hard to think of somebody in music that goes on to Juilliard that hasn't had some development, some ship legs underpinnings along the way. Whether it's in sports or most endeavors, you've got to think about the market, the pool that is going into that pipeline, and which is a part of your sustaining need in your enterprise. Some of the other constraints are driven by the expectations and opportunities. You live in the brightness and the shadow of those sometimes. What are the expectations? What are the opportunities? And how are they associated with national priorities? And also an awareness in this whole scientific endeavor of the demographic and workforce issues. There's some new, well, there's some changes, demographic changes that are enormous, and I'm not so sure many of us in the science enterprise that we represent are fully aware of those. Now, if you look at the market from which we draw, this would be any corporate type, a business type organization trying to advance a cause, you would look at the market, the base upon which you draw and are trying to affect change. It's enormous in education. We're talking about enrollments that you see there in the millions. And so this is, one has to have a feel for this. There's opportunities here, but there's also challenges because it is so enormous. It's like trying to do a piece of research and you have this incredible body of background in information. It's often hard to really go forward and wrap your arms around it. But this is very telling. These next few slides, I think, hopefully will bring forth why we have to go forward with all deliberate speed. This data comes from the National Center for Educational Statistics. Leela and I have talked about this, and many of you are familiar with it. Jill, I know, is also. But most academics, I'm kind of surprised, they don't know about this. This is terrific data in the sense that it comes from the Office of Institutional Affairs of each university. The 4,000 plus universities that we have in this country have to submit this information. And it's been going on for decades. It's a very deep, robust data set. And there are benefits to do department chairman surveys and so forth, but there is a little bias and validity problem sometimes with that. This is a little bit more independent, and I want to have you take a look at in the life sciences. This is the one area of science in the country that through many, many different measures is doing very well. And you can see the bachelor numbers for the past 30 some odd years here. These are the degrees in biology, life science. We'll also put micro and zoology, small subsets of it, but you see they've doubled. These enrollments have doubled at the bachelor's level. When we take a look at the physical sciences, and this is what has a lot of people in Washington and town here that Jill and I interact with quite a bit on different committees, and this is what has a lot of people concerned. When we take a look at that same period of time, that 36, 37-year period of time, the bachelor's degrees are down. Bachelor's degree in chemistry, they have turned around though. Here's the bachelor's degree in geoscience. You can look at these in more detail because they'll be available. We're still going down. Physics dropped, but has turned a corner. This is very interesting. Now, we have gained here, and there are some workforce issues involved in that, showing you where people are coming from, maybe not so much with the bachelor's degree, but going directly into the master's from some other programs. But what's really staggering about all these data sets, when you take a look at all these numbers, here are the degrees starting at the bachelor's level, say, and during this 30-year, 36-year period of time, when you look at the undergraduate collegiate enrollment, again, of these 4,000 plus universities, the undergraduate enrollment has doubled, more than doubled during that period of time. So when you hear the statistics being thrown out, and I've used it all the time, we have less than half the number of students in our country as a percentage majoring in science than we did 35, 36 years ago. That's troublesome. Added to that, some confounded variables that we can put on top of that are some of the demographics here. When we start looking at, this is also from the National Center, the IPEDS data, National Center for Educational Statistics. If you look at African Americans, the underrepresented groups, Native Americans, Hispanic, these are the total enrollments, the graduates. These are the graduates for the year 2007 in the geosciences. Physics makes us look pretty bad. And so these are in the Hispanic, here 135 out of 4,000 bachelor's degrees. In the geosciences, only 135. When they're getting to be large, over 25% of the population and so forth, we are not doing very well. All of science isn't doing particularly well, but we're on the bottom of the heap. That has some implications for us. We have to be aware of that. Now, let me just say quickly on some of this. We, in 1995, came out with the national standards for science by the National Research Council. For the first time, earth science had full parity with physics and life science. And it's really remarkable. It was the physicists and the chemists, many of whom were Nobel-level scientists, instantaneously understood the importance of the earth sciences. It gave context and meaning. It had to be in there. Now, we can see, this is from the data from the Council of Chief School Officers, what you can see here is when those standards came out, about 1995, 1996, the number of earth science teachers from the Council of Chief School Science Officers who state by state track this, you see the bump up. Correlation's not causation, but it's hard to interpret this any other way, that those national science standards were having an impact. Now we've dribbled down. In comparison, where is chemistry? This is for 2006 data. Chemistry is at 29. Biology leads the pack always at 59,000 teachers, 22 for physics. But what's interesting here with physics, you saw how the bachelor's numbers went up. Here's a number of physics teachers in 2000, 15,500. In 2000, only 15,583. Look at the enormous jump that the physics community has made on physics teachers. They have really put a lot of effort into that, have programs and in physics education that's paying dividends. And here's just a quote that says, you know, biology state data on science courses show that in most states, all high school students take biology, while across the states, enrollment in earth science at the high school is extremely varied. If you look, even with that enrollment of the 16,000 that we have, it actually swells, though, larger than all the professors. I pulled the last printed edition here of the of AGI's directory. It's now a wonderful resource online, but I keep the dates, the '07 data consistent here. Had tenure track professors, associate professors, and assistant professors, about 12,000 in the academic core. So it's actually, when we talk about those secondary teachers, just 9 through 12 in earth science, it's actually much larger. So that's our advanced guard, getting our information out in that national literacy realm. And we know GeoTimes, AGI's Earth Now magazine has had wonderful articles over the past 5 or 6 years on the problems we face. Always a rear guard movement trying to get geoscience back in. And this is really something that has hurt us dramatically. AGI, USGS, other professional organizations have constantly had to jump into this. Now, we have had 20 years of standards. We have had benchmarks, science anchors, and now, moving on to new Common Science Ed standards initiatives. But they're only as good to the extent that they immediately degenerate into hard work. Something has to come after that. This was a catalyst. No teacher goes in and uses the standards. What they use are derivatives of the standards. Good instructional material, up-to-date, timely, accurate material. There's a lot of stuff out there, but whether or not it's doing the job is a question that has to be asked. Otherwise, we're just putting old wine in new skins, one more round, but not getting at the core of the problem. What's worth taking a look at is something, and I think this is worth rediscovering. Back in the Earth Science Curriculum Project, this was the last of the great large national funded NSF projects, the Earth Sciences. And on the board and directly involved were great scientists. On the board of this program was J. Tuzo Wilson, a name that's familiar to all of us. Rachel Carson, Dick Johns. These people were integral. So the science and the educators and the best learning theorists this time were really putting out projects. And most of what we've worked on at that secondary level has been poor derivatives of what came forth during that golden era. And then just finally something to think about. This is from not the Department of Education, it was the Office of Education that in 67, 68 did the first assessment of the number of students taking earth science. And I found this in the files. It was like finding some long lost piece of information that brought some thoughts back here. And I'd like you to think about it in my closing slide. They estimated, again, it wasn't a department, United States Office of Education estimated that at the 9th grade, so secondary and above, 9th grade level, that the enrollment in earth science of our students was 26.2%. The best handle we can get on what that present day enrollment is something from a high single digit to a low teen. So I think it's worthwhile to think back at what worked and what went forward after they had standards, a hard, solid, useful, and well-received curriculum. Well, thanks for listening.
Thanks, Jill and Chris. And we're going to take the next 15 minutes and field some questions from the audience. I'm going to go ahead and everybody here. Just to kick off the panel discussion, hold on just one second. Just to kick off the panel discussion, one thing I wanted to ask all of the speakers was, taking a look at the science literacy initiatives, looking at the College Board standards, and looking at how that's been worked on over the past few years, could you comment on actual implementation of these initiatives for the future? Implementation either at the state level for standards that are required of all K through 12 curricular activities, or through college, or at a federal level. If you could kind of detail some ideas for specific things we can look forward to in the future as a result of all these things.
I can go first if you'd like. The one thing that I think will help with driving some implementation is this National Academy's Roundtable for Climate Change Education. The process that they're engaged in will invite not just academics, but like a normal academy study, but a roundtable can be composed of people with expertise and also be federal employees from the agencies, state and local stakeholders in the issue. And I think that as a result, there will be better engagement with those who have to make the decisions at a more local level, and not just sort of the federal, not just the federal perspective. And just as the literacy frameworks were developed with a lot of dialogue with the community, which helped to get them vested in the use of those frameworks, I think that the Academy Roundtable will help get some, vested interest on the part of those who make some of the state and local decisions.
I would just add that from the College Board side, states are constantly coming to us and asking for help with aligning their state standards to different frameworks. And now that we have our own framework and that it outlines very clearly what a student needs to know in earth science at the middle school level and the high school level, as well as kind of at first year level college AP classes, we now have something to measure them by, and it will be very useful, and we're just at the very preliminary stages of doing this, but hopefully in the future this will become very useful to states so that they can see where the gaps are between their state standards, not only in earth science, but in all the sciences. So.
And I've found that many of these initiatives, like curriculum initiatives themselves, when they're not maybe they're not a national curriculum, but at least they're nationally developed, they serve as a wonderful in-service for teachers. A lot of things since, say, the national standards came out in many areas, but just like climate change, I don't think we mentioned a heck of a lot when the national standards came out in '95. Well, it's, as Jill is indicating, that's a beautiful, that's the exemplary Earth system kind of big idea. So this can really help keep the practitioners, the teachers in the classroom, updated on what they need to know and what the relevant topics are and how best to address them.
The other comment I wanted to make with regard to implementation is as I mentioned, a lot of the funding agencies are requiring references to these literacy frameworks in proposals that we're funding. And so although the big ideas in those frameworks may not be explicitly, articulated, the resources that are being developed are intended to support those basic messages. And so I think there will be a diffusion, even if it's not so explicit, in getting those big ideas into whatever educational materials are being developed.
Great. We've got a couple more questions from the audience, and just a reminder to all participants, you can go ahead and ask your questions by typing them into your question box. So here's one question from the audience that says, recognizing that there's a critical demand for geoscientists and that the current production of geoscientists is insufficient to meet that demand, why does the College Board not promulgate AP courses and exams in the geosciences such as geology, meteorology, oceanography, and astronomy?
So I guess I can start with that. And I think it's a very good and valid question. Things tend to move a little slowly around here, and I would say that really the focus has been on redesigning the tests that we have had. Several years ago, the NRC put out a report kind of criticizing that what the College Board was doing with AP was actually a disservice because we weren't really pushing education forward, and it was kind of the best thing that was out there, which is why people relied on it, but it wasn't by no means the best thing that we could produce. And since then, we've gone through this redesign process, and we're really focused in currently on the sciences that we have already had. And once we can kind of get a proof of concept and get that up off the ground, I think that there would be a bit of an appetite for looking at this differently and seeing what other courses we could add, especially now that we have a standards base to kind of back up what we expect students to be able to know by the time they reach college.
There's also an element here, perhaps in the question which I picked up on, maybe it wasn't intended, but I think there is a employment, a jobs component to this. Where do we go? Where are the science jobs in the future? What skill sets and understandings do students have to have under their belt? We tend in the professorate and academia to kind of clone our own, but ourselves. But the green jobs, what are the skill sets that are needed for those jobs? Where are those jobs? And I think you're going to see, I mean, in this town and the nation, that's the big issue, right? Is jobs, 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 and turning the economy around. And we have to build that connection. Faculty, state universities in former days had a much better finger on the pulse. Many faculty worked at U.S. Geological Survey or worked in industry, and there was more of a flow back and through, back and forth between industry and government agencies and the academy. Right now, most people in academia have been born and bred academia. I'm not sure we've got, as a geoscience community, our fingers on the pulse of where those employment opportunities lie, which in turn should inform instruction at some level.
I think there's also a sort of a catch-22 issue here. You know, a lot of this depends on what the institutions of higher education value, and if you know, we could argue for more inclusion of earth sciences at the high school level, but if those courses and credits are not valued by the colleges in admissions decisions, then the students are less interested in taking those classes. So you kind of have a chicken and egg problem of generating the interest, showing the value of those courses, and then having an audience to be receptive to valuing them. I was at a conference last week that was part of the American Association of Colleges and Universities and Project Kaleidoscope, talking about sort of the next 5 years of undergraduate STEM education. And it was very interesting because they were all pretty much in agreement that the wave of the future is increasingly interdisciplinary STEM education at the undergraduate level. And I raised the question of, you know, whether, you know, how to sort of handshake those changes that they might be contemplating with what the AP, you know, redesign effort is focused on. And they agreed that there needed to be more thought given to how to do the articulation between K-12 and undergraduate. And so I think there might be some opportunities coming down the pipe.
Got some more questions here. This one pertains particularly to the College Board standards, but I'd like to also ask it as a more broad concept. And the question is, have you considered engaging non-academics as reviewers of the standards?
I'll just start with that again. Yes. In fact, when we went through our review process, that was the case. We did have a few groups. And I guess I'd want to know exactly what they mean by non-academics. But, you know, I think that we tried to get as diverse an audience as possible to review our standards before we put them out, and we felt pretty comfortable that the group that we had put together was quite diverse. So.
Another question is, what can stakeholders or teachers in the states do to promote the earth sciences, since much of the decision-making is done at levels far above us? Or should we sit and wait to see what happens at the national level?
I think action has to be taken at the local level. You know, I'm a federal employee, so I can't really advocate for anything, but I will point out that you know, there are organizations at the state and district level that maybe are unaware of the relevance and the sophistication of this field. You know, again, because few people have taken earth sciences themselves, I think they have strong biases about what the course entails, and, you know, the sort of the classic rocks for jocks kind of image, and, you know, the remedial science. You know, we have an image problem at some level. And so I think, you know, local educators can begin to talk to their communities, raising their awareness of these frameworks. They can, you know, talk about the importance to the workforce. They can talk about, you know, the national need, et cetera. But I also think that they need to be, there are times when I've imagined sort of the equivalent of a soccer mom movement amongst the earth sciences education community to kind of create some buzz at the local level. I often ask myself, why aren't our students learning these things? I would think most parents would sort of, when they start thinking about the hazards and the resources and the economic dependence on earth science phenomena, that if they knew more, they would begin to be shocked at the fact that their students, their children, were not being educated on these topics.
Mm-hmm. Yeah, I agree. I was thinking of one of the things that we need desperately is, in many of the state levels, my experience with state boards of education and so forth, they generally buy into the importance of the earth science when you bring a team of people in and you talk about. But some of the material then, as far as looking at it, this is what we face a little bit in California, that some of the material doesn't appear to be secondary level material in rigor compared to what a board member who probably doesn't know a carbon cycle from a unicycle, but he's looking at this stuff, and it seems that what he's looking at in physics and chemistry, that what we have in the earth sciences doesn't really cut muster. But I am always impressed at what can be done at the local level, and we do have good people. They were in Texas, and they are in California now, and virtually every other state that are good proponents, constantly making the case.
Great. We've got a couple more questions here, so we're going to continue on. What are your thoughts with distinguishing standards between environmental science and environmental studies?
I'm not sure I understand the question. The distinction between environmental standard, or the environmental studies and environmental standards, or?
From what I understand,
studies.
Yeah, between environmental science and environmental studies, as those are sometimes taught as separate programs and sometimes combined. So is there an idea for distinguishing standards between those two disciplines, environmental science and studies, or putting them together?
Well, I just want to say one thing here. I think that all too often we look at standards and we think in very traditional terms, right? So if you have some chemistry concepts, those go into the chemistry class and they're taught only in chemistry. And same thing with any of the other disciplines within science. And I think that's really not the best way to approach this. And one thing that we really tried very hard to do, especially in the front matter of our document, is to say, look, we're not saying that you absolutely must have an earth science class at the middle school level and another one at the high school level. We're saying that the concepts and the content must be included in some science class. If that's a general science class, great. If that's physical science, that's fine too. If it's earth science, it doesn't really make a difference. It's just all of that has to be contained. And I think all too often we kind of, we tend to put science in all these different silos, and students end up learning these things as if they're independent of one another, and they're not. And if we really want to have students practice science in the way that scientists practice science, that's not the way to do it. So.
Yeah, and that was one of the, I think, beautiful things that came forward from the AP redesign. It wasn't just the course, the AP course itself. It's what you had to have under your belt all along to get ready to do AP work. We brought it, you could bring it down into the kindergarten level, I'm sure, but just to make something that was workable, wrap your arms around, we start at the middle school level. So it's a sequence of these understandings that students should be exposed to and have some working knowledge of to do justice to an AP course. How they get it, where they get it, whether it's in an interdisciplinary course. This has been the, this has been the gold standard. When we were in 1992 starting the National Science Education Standards, everybody was talking about this too. This was the holy grail to somehow really bring an integrated 4 years of science or 12 years of science forward. Everybody realized the benefit of that, And as you look at cutting-edge research today, our research is so integrated, it's really hard to separate what some of the subdisciplines, even in geoscience, are that contributed to a particular piece of research. But we still have, you know, this compartmentalized subdiscipline kind of categorization that is cultural, I think, in this country more than anything else. But yet, to the extent to which we can get good examples of a systems approach, which just by its name inherently is going to bring in all fields of science, typically, that's what we should be pushing for.
Great. We've got two more questions here. One is pertaining to Canada, and it reads, in Canada, education is strongly in the hands of the provinces, and we lack national agencies that lead the way with curriculum, science, earth science, and otherwise. In the U.S., which agencies are strong national voices for the standardization of curriculum?
Definitely the states. it's the states, but yet at the same time, we saw in post-Sputnik era here, where we did have, and I use that term purposely, nationally developed. I mean, nobody was pushing anything down on the states, but if you had great cutting-edge material, well developed, build it and they will come kind of philosophy. And I think we're seeing in this administration sensitivity to that and favorability to that kind of approach.
The other aspect is that not all states are created equal, and although it's true the states have control, there are certain states that tend to drive the development of some of those curricula because of the sheer volume of numbers of students that they have, and that's New York, Texas, and California.
Florida too. Yeah.
Well, yeah, and so if you can get them on board, they can help steer the ship quite a bit on what gets developed. What's been interesting is that this move towards and it's exemplary, it really is, this move towards common math and language arts standards that's been going on in the last year or so has been driven by the state level education offices and an agreement that maybe we ought to have some common core standards. And this is where this common science standards effort has sort of piggybacked off of that thinking with the support of state level science supervisors.
Mm-hmm.
We've got one last question here, and it reads, how are we going to get Latinos and African American students to take these courses and continue on in college? Latino parents don't always find fieldwork appealing, especially if they worked as migrant workers.
Yeah, it's something we, and as part of the Department of the Interior, we're very concerned about that. One of the hidden are these crown jewels of our nation, the national park. The attendance has dropped something like 25% in the past 5-6 years. And this is driven by demographic changes, actually, largely, as far as we can interpret, that getting students outdoors, a lot of issues here with type 2 diabetes, and not going out, exploring the out of doors is a major endeavor for the Department of the Interior. And also to bring these students out into the natural world, which I'm always amazed at the number of scientists that talk about how they first got interested in science by being out of doors. Richard Feynman, the great physicist, talked about that. His days up in the Catskill Mountains, and how looking at nature, interpreting, observation, interpretation, which is best done in the out of doors. That's the grabber. Was the catalyst for his interest in the natural sciences. So these are challenges, and we in the Department of the Interior, for instance, have this big youth initiative. That's one of the major priorities right now of this administration and our secretary.
One of the programs that I manage is the Opportunities for Enhancing Diversity in the Geosciences program, and the solicitation is currently expired. There will be another one issued this summer with a competition in the fall. And we are trying to address these very issues. Based on some of the previous awards that we've made, however, I think it's not, there's a lot of opportunity actually to engage underrepresented communities, particularly when the focus is, the connections are made between earth sciences and community. And the the fact that you can be involved in earth science related research and work that helps to support your community, and which tends to be very very appealing to many minority communities. One of the really critical things, and I want to wind back to something that Bob was talking about, is the fact that many underserved communities have very poorly trained teachers with regard particularly to earth sciences. So if it's being offered at all, you're working with educators who may have the weakest preparation for teaching that subject. And given the subject here about departmental sustainability, I think it's really important that university departments recognize that many of the students that they are have in their introductory classes are future, they're pre-service educators. And I think the tendency, and this is of course a gross generalization, but the tendency is to focus on what your future potential majors may need in those introductory classes or recruitment of majors, when in fact the greatest impact you may ultimately have is on helping to strengthen the training of future teachers who will then, encourage students to go on into this field down the road. And I think that responsibility should be, really scrutinized in the individual departments as to whether they are really adequately serving that additional goal.
Yeah, I think that's spot on, Jill. One of the, we're an interesting science. I can't imagine a student, say, majoring. Let's just take majors for a moment. I can't imagine a student majoring at a university, say in physics, without ever having a physics course in high school, or chemistry. But our departments are largely, this is how they get their majors. Kids stumble into, how many times have you heard that, right? Kids stumble into the geosciences and they kind of fall in love with it. I like it. Well, that speaks volumes, I think, for the inherent interest of our science and also the quality of the teaching by and large. But what a heck of a way to run an airline, right? So I think the way in which we can get more of our best and our brightest to get into that, to have a stint. They don't have to do it for the whole life. That Teach for America is a wonderful model to put some time on task and on these these pipeline issues, on the advance of the early students. I think would pay enormous dividends, both for the instructor, skill sets that they learn, and so forth, as well as the whole need of the profession. Are we still there?
Just had a little bit of a audio glitch there. It's fine. We're back on. Well, that will conclude our questions for today. And if you have any questions that were not addressed today, you can email them to us at workforce@agiweb.org. Be sure to check back on our webinar site soon. Here at the bottom of the screen, www.agiweb.org/workforce/webinars.html. We'll be posting this recorded webinar on our webinar site soon, and you can visit and view this at a later time. Also, just to let you know of upcoming webinars, we will be having a geoscience currents discussion next week, February 2nd, discussing K through 12 teachers and geoscience degree backgrounds. And then in March, we'll be having another GeoConnection webinar. It will be the first in our career series focused on geoscientists in the media. And again, you can get the information there on our GeoWebinar website. And I just want to thank Jill and Chris and Bob today for taking the time to speak at this webinar. And this will conclude our webinar for today. Thank you, everyone.